landslides in New Zealand triggered by rainfall and earthquakes. So just before Martin starts his presentation, 2 points. So from the housekeeping perspective, please use the chat function within Teams to ask questions, which Martin can respond to at the end of the talk. As I said, the talk will be recorded and it will be available afterwards on the BSG's YouTube page. And the second talk in June, run by the BSG and EGGS, is by Mark Lee on the 24th of June. And he's presenting on geomorphology, geohazards and energy pipelines. So with that, I will pass over to you, Martin. Thank you very much.
Thanks, Paul, and thanks for inviting me. It's a real pleasure to give this talk. I'm part of EGGS, and I used to be part of the BGRG as a student before it was the BSG. So there we go. Today I'm just going to talk to you about some of my research in the last 6, 7, 8 years at the University of Auckland, primarily by my research students. I've got to admit, I'm usually stuck in the office teaching or marking or doing something boring, but I do get out now and again, and I always help them write it up and publish. So I'll take you through a few things today. I'll focus on 3 case studies actually, and then there's some lessons right at the end that I want to quickly go through as well. So this is just a bit of an outline. I'll give you a bit of an outline about the geology, geomorphology and climate, and about these multiple occurrence regional landslide events or MOLIs that we have. And then those 3 case studies, Kaikoura, some Gisborne ones and Auckland, and then just to summarize the problems and maybe a few learnings right at the end. Just a bit about the geomorphology and geology. I like this one, but these 3 diagrams together, I use them in the lectures actually, but on the left we've got the basic geology of New Zealand, and if we think just about the North Island, the white here, the sediment cover, this is neogene, mainly marine materials, sediments that have been uplifted, often mudstones. These are weak materials, often 5, 10 MPa UCS. And then this dark grey is the grey wacky of the North Island. And then we've got the volcanic rocks in purple here, and also some in Northland as well. But mainly the materials I'm going to talk about today that are a problem on the North Island are these weak neogene materials here, which are Pliocene and Miocene. Some Miocene rocks around Auckland, and then some older rocks here on the South Island around Kaikoura. This middle one just tells you a bit about the topography. So in the center of the Southern Alps, that's where the highest mountains are, over 3,500 meters. And then we've got some decent sized up North Island, the actual ranges here of the North Island, which are grey wacky. And then we've got mean annual rainfall here. And there's a very strong southwest northeast climate gradient in New Zealand. So the southwesterlies bring a lot of rain to the southwest, and also the west coast of Auckland and the western side of the North Island. And generally, the eastern side of the North Island is generally much drier. But in a period 2019 to about 2023, it was exceedingly wet. And it's probably to do with atmospheric circulation in the Pacific and some other factors. So yeah, that's sort of general picture of New Zealand, just to outline, where everything is. I'm sure some of you've been there anyway. I've read a fair bit about it. Just a bit about the seismicity. This is a bit dated now, and I've superimposed the Kaikoura earthquake of November 2016, because I'm going to talk about it in a bit. That was 7.8 at a town called Waio there. And you can see lots of earthquakes around the plate boundary. So subduction westwards here, subduction eastwards here. Quaternary uplift rates around Kaikoura are quite high. And also some quite high uplift rates around Gisborne, which I'm going to talk about as well. Auckland is a long way from the plate boundary, so we're not too affected by earthquakes there. And uplift is negligible, I guess. Yeah, this just summarizes that nice recent map by Hirschberg and Sutherland showing you all the strike slip tectonics, especially in the upper South Island, lower North Island. So just a bit about these multiple occurrence regional landslide events. This is what me and my students have been working on, my research students, the last few years. I don't know, it might have been Mike Crozier who came up with this term at Victoria University in Wellington, this Morley term. And on here, I've just shown on here some significant earthquakes and storm events in New Zealand that have occurred since European settlement. So multiple occurrence regional landslide events, they're a real problem in New Zealand because instantaneously or within a period of a few hours, you can get several thousand landslides occurring. So that could be rainfall triggered or earthquake triggered. And that's a real problem for society to deal with immediately. And also it tests the resilience of infrastructure. So water pipelines, roads, etc. And since European settlement, we've had lots of Morley events. Most recently, we could talk about Cyclone Bola 1988. That caused some damage a lot of damage in Hawke's Bay. Manawa 2 storms 2004. And then particularly, the Kaikoura earthquake in November 2016. And then more recently, in Auckland, we had the Cyclone Debbie and Tasman tempest in consecutive months, 2017. And then in Gisborne, really, from 2019, but particularly from November 2021 to February 2023, and even beyond that, we've had a lot of major storms in Gisborne on the northeast of the North Island. And Gisborne's an interesting place because it's quite, it's got a lot of social deprivation. The infrastructure isn't resilient enough, and it can be easily cut off. So that's a real problem, Gisborne. It's very susceptible to landslides, and that's not going to be solved anytime soon, that issue. So this is Hawke's Bay after Cyclone Gabriel, February 2023. On this is from NewsHub, but I think Tom Robinson at Canterbury actually did this mapping. But we've got between 200 and 600 landslides per square kilometre in some parts of Hawke's Bay after that event, and you can see just looking at the Neogene tilted sediments, you can see channelized failures, you can see open slope failures, so it's no surprise that you get into between 200 and 600 landslides per square kilometre. And obviously this is in the middle of nowhere, but it is a problem. There's a lot of downstream cascading effects, and also once the soil is gone, the farmer's pasture is then gone, so there's no grazing land, etc., etc. So it's a real problem, the amount of erosion that goes down the rivers, and then the aggradation and engineering problems with stop banks and all the rest of it. So a lot of cascading effects, even though this is quite a rural region. And it's not the first time it happened. March 1988, Cyclone Bola did pretty much the same thing in Hawke's Bay and the Gisborne area. So these events do come, and often it's an extratropical cyclone, just making landfall on the northeast. So it might come down from the Coral Sea, and then makes landfall in the northeast New Zealand and causes these kind of effects. Muriwai, Auckland. This is February 2023. Cyclone Gabriel there hit Auckland first before it moved across to Hawke's Bay, and a lot of damage here in Domain Crescent in Muriwai in West Auckland. This is a sand escarpment, Pliocene and Quaternary sands, and lots of devastation there and some fatalities as well. And these effects in Muriwai are not new, because in 1965, in exactly the same part of Domain Crescent where houses had been rebuilt, there were fatal landslides as well on consecutive days. And I'll get on to what was rebuilt and why in a minute. So I'll just start on these case studies and I'll take you through. This is mainly Caleb Gaston, one of my PhD students. It's mainly his work I'm going to show you. which is just finally submitting for publication, I think now. So the Kaikoura earthquake, 14th of November 2016, we felt it in Auckland. It was around midnight, and I remember I was still awake, and some of our light shades were shaking. So it was a major earthquake, and this caused damage along 180 kilometers of coast. This area, especially the southern Kaikoura transport corridor. There were a bit of subsidence, but also a lot of uplift, up to 6.5 meters, maximum of about 12 meters horizontal displacement. And the recent work that Chris Massey and colleagues have just published in Landslides journal, I think they identified at least 31,000 landslides. And just to give you an idea, 72% of these Chris characterized as soil or rock and/or rock debris avalanches in Cretaceous Pahau terrain, grey wacky or grey wacky derived materials. So that could be colluvium or residual soils derived from the grey wacky. There was also a lot of secondary landslides and reactivations. So here's Kaikoura, and the main highway, State Highway 1, and the railway go along this narrow coastal corridor, and there's not much accommodation space. So that's a real problem, keeping the road and the rail open there. And these are very rapidly uplifting ranges. This is from Colin Bloom's work, and that's the epicenter there, just near the town of Waio. And my student Caleb, he got so into his research that he actually moved down to Waio, bought a plot of land, got a house built very quickly, and really embedded himself in his field site. And he was one of those great students, the commitment to the research. So good on him. This is one of his thesis chapters. This is the seafront landslide. So this is in the Eocene-Amuri limestone, and the Papatia fault goes through underneath. It's obscured actually by this displaced mass here, but it roughly goes along here. You can see this cross section that Caleb put together. There's the Papatia fault, and these rocks have all been overturned. And I think the first time Caleb went down there and started mapping, he realized very quickly that everything's been overturned over millions of years. So that was, so this is the Amuri limestone here, and we're younging downwards here into the Whalesback limestone, etc., etc. So a lot of interesting units. And to give you a bit of scale there, the headscarp there is about 150 meters high. So this is a very large feature. This is what it looks like on the ground. There's Caleb looking at some of the displaced features and some of these thrust up wedges of material in the toe area of the landslide, or what's left of it. Caleb was lucky enough to get a borehole done through the landslide, which really helped him constrain the rupture surface and some of the other features. So he identified at least one rupture surface at 47 meters depth, I think, some fault gouge, etc., etc. There were a lot of problems, obviously, drilling into a big landslide like that. It was during COVID as well, so that was not a great situation. But this should be published soon, hopefully. We also did some electrical resistivity and P wave velocity down the landslide to try and help constrain laterally the borehole. So ideally this would have been peppered with boreholes. It should have been like a Swiss cheese, but just the cost of putting boreholes into landslides, it's very problematic and costly, obviously. But the resistivity was quite useful, I think, for Caleb, and also the P wave velocity, the refraction work that we did there in helping constrain his engineering geological model. Another landslide Caleb looked at, another big bedrock landslide, was the Leader. And again, just to give you an idea of scale, this scarp area is about 200 meters high. The P is the primary landslide and the S is a secondary landslide. Like a lot of big landslides in New Zealand that were earthquake generated, it blocked the valley and a landslide dammed lake was formed, which you can see here, and it's quite turbid. And this was in Pahau terrain, grey wacky, and also Greta Formation siltstone, formed right at the daylight, well, basically where the Humps Fault South Strand daylights, that's where the landslide has occurred. And this is a cross section of the primary failure. This model was put together from boreholes, geophysics, as well as exposures in stream beds and cuttings and scarps. So this is Caleb's take on the primary landslide, and this is his take on the secondary failure here, across here. He's identified a couple of failure surfaces in that secondary failure. I think this is going to be submitted for publication soon, hopefully. This just shows you a bit more detail, and again, the stratigraphy there has been overturned. Like a lot of that really deformed part of central New Zealand on the upper South Island. So we've got a cross section here, which shows you here the Humps Fault North Strand and the South Strand there, and then the North Leader Fault Zone. And here's where this Leader landslide formed, just here, and there's the displaced mass, that red deposit there. Again, Caleb was lucky enough to get a borehole put through his field site there, and he managed to identify some fault gouge there, some basal rupture surfaces as well, which helped constrain his geological model, and also highly plastic clays, cataclassite, other classic materials representing faulting and also landslides. And there's some examples here, some cuttings that he managed to get into in the toe there. Some resistivity here, and again that helped constrain when you've got limited boreholes and limited exposures. Geophysics can be really useful. So these some ERT here and some P wave velocity here to help him constrain what was going on. And very complex subsurface, essentially, is what he found. And here we've got particular failure surfaces in that Greta formation identified. I'll just move on now to the transport corridor at Kaikoura. And so here's Kaikoura Township. And there's a Kaikoura North transport corridor towards Clarence, and then the South corridor here. This is what I'm going to focus on, and I had a research student, James Stringer, work here, and it worked out quite well for him, what he was doing. He worked in with Golder Associates, who were involved. They were one of the companies down there, or Golder as it was at the time, now part of WSP. So he did a bit of work down there, which worked out really well. This is what happened along the coast. There's an uplifted shore platform here, and you can see along here uplifted areas. This white line here is a good marker of where the uplift has been, and you see how this slope has collapsed over the transport corridor. This is typically what happened, these kind of failures in the rock slopes there. Here you can see the train track. It's just broken like Meccano. It's been transported down across the state highway and onto the shore platform, and the shore platform's been uplifted. This is all fresh uplifted area, dark here. The rail here has been affected here near this tunnel, and badly affected by this rockfall. So this is typical of what happened. Cones of material coming down, often channelized down, wedge failures, and affecting sometimes just the rail, but sometimes the State Highway 1. So this is the main road, State Highway 1, and obviously it's just one lane in each direction. It's not like a motorway or anything, but it's extremely important. You can see very narrow accommodation space there, here. Some of the work that James did and other people he was working with tried to classify the rock mass, essentially. And they came up with a three or fourfold classification scheme. And there's three or four examples here. Class 1, defect controlled wedge failures. Class 2, this is all in grey wacky, by the way, defect controlled outcrop here. This is towards the top of the slopes, and it's heavily dilated rock mass. So during the Kaikoura earthquake and prehistoric earthquakes as well, obviously the top of the ridges well, they don't flap around like this, but there's no lateral support at the ridge top, so the rock there tends to become very dilated and weak, and it looks like this. And this has been like this class 3 here, this other class 3 here at the top of a slope. You can see how damaged it's been by many earthquakes over probably hundreds, thousands of years, not just the Kaikoura earthquake. So obviously stabilizing slopes like this is a real problem. This is just from James's thesis, James Stringer's thesis. This is the area that he was particularly interested in, south of Kaikoura. And he looked at these 3 landslides in particular, SR29A, SR26, and SR12 here. So you can see the transport corridors right along the edge of the Pacific Ocean here. And you can see, just looking at the topography, probably lots of landslides in the past, very undulating landscape. James did a lot of DM differencing using UAV, terrestrial laser scanner, LiDAR DEM surveys. There were also survey prisms that were installed as well to monitor deformation. And James also was involved in a lot of telemetric monitoring, extensometers, tilt meters, tripwires, and also a series of GNSS nodes, which I think were 20-minute intervals. So this gave James a really good handle on these landslides and what was going on with the slopes. I'll just give you a quick rundown of some of these. This is landslide SR12, displaced bedrock outcrop there. This was a rotational landslide, according to James, in colluvial soils and underlying Greywacke bedrock. It was triggered by the earthquake, and then there was a secondary translational failure of colluvial soils and a bit of toppling as well. And you can see it's been cleaned up, but that obviously is displaced across the road. Landslide SR26, this is a bigger one from the ridge line extending really the full height. There was only minor displacement here during the actual earthquake and some tension cracking. The main failure actually occurred a few weeks later in December, actually during dry weather. And that caused a major detachment, and this landslide head block came down and arrested here. So obviously the months that followed, there was a lot of concern down on the road with all the work that was going on to rehab the road and get everything up and running again, that this landslide head might become detached by an aftershock or another storm and end up down on the road. So this had a lot of monitoring installed on it that James was involved in, and it's all in his thesis anyway. And this was in colluvial soils, but also the underlying weathered Pauhau terrain Greywacke, which is what you can see here, and some further Greywacke blocks. In fact, this is the top of the landslide head here, and you can't really see, but there's a very faint line there, and that's an extensometer cable. Some DM differencing. So this one on the left is from July 2012 to just after the earthquake in November 2016, and you can see there'd been some movement of material during the earthquake, but not much. And it was really this survey which shows the difference between just after the earthquake and May 2017. The major displacement actually occurred here in the December, so a few weeks after the earthquake. And you can see, a lot of material transferred from that headscarp area at the top of the slope all the way down slope. Some of it displaced to here where that landslide head is, and other points as well where the material self-arrested on the slope. Some of it made its way all the way down to the road. This is some of the equipment James installed and helped install. So this is the AccuM GNSS system with nodes, base router, and internet to send the signal, with a radio antenna there. There was a lot of other equipment up there, string pot extensometers, string potentiometers, survey prisms, all sorts of equipment wired up there to monitor that landslide head area, to make sure that the workers were safe down on the road and allow the rehab to occur. this shows some of this, and I won't. This is just a fragment of James's work, but it just shows some of the effects. We've got these bar lines here are rainfall amounts, and you can see Cyclone Gita brought about 120 mils in a day, which potentially would be a problem, but she didn't tend to have any effect at this SR26 site. But there's some interesting other things, and this is a good example of why you should always have several different monitoring tools in combination. Here, this is where I think a possum ran into one of the cables, one of the extensometer cables, and you can see it shot up. But you can see that the GPS nodes, GNSS nodes, are showing no deformation at all. So it just shows, the effect of wildlife sometimes on extensometers. So I think from James's standpoint, it's very good that he actually had a few different tools, monitoring tools that were working in combination to try and understand what was going on. But the survey prisms, show gradual downslope movement over time. Right, so that was Kaikoura. I just want to move on to the second case study, which won't take a few minutes. Gisborne, rainfall triggered landslides from around 2019 to 2023. Gisborne is a city northeast of the North Island here. It's a city. It's 38,000 people, but that is a city, believe it or not, in New Zealand. It's in Gisborne. You see the intersectionality. I know that word's used a lot in social sciences, but it's really applicable here. The intersectionality of a lot of different geohazards. You're close to the subduction zone. There's a lot of uplift. It's exposed to tsunami. Mud volcanoes occur. There's a lot of expansive soils, and also a lot of landslides and associated flood events occur too. So it's really vulnerable to landslides on account of generally the steep slopes, young soft geology. So quaternary, Miocene, sometimes Miocene strata, clay-rich expansive soils, a lot of deforestation, a lot of slope cutting, a lot of filling, loading of slopes, some dodgy retaining walls in suburban areas that aren't built to code, which cause more problems. And around a metre of year of rainfall, but some events can bring over 200 mils in 24 hours. These black dots, these are just landslides that Matt Cook in his PhD identified using his INSAR, and he published this in about 4 or 5 papers over the last few years. And just closing in a bit on Gisborne, these are all Gisborne suburbs, and you can see the suburbs expanding out into the hills and into a lot of areas of landslides. This is looking from Captain Cook's monument westwards. Gisborne is at the confluence of the Taruheru River and the Waimata River, and you can see lots of building on the floodplain, but also gradual building on the terraces and also on some of the toe slopes as well of some of the bigger hills around the periphery. In rural Gisborne, this is the kind of landslides that you see. This is from Sam McGovern's research project. This is Miocene Tolog group, mudstones and siltstones, tilted strata. You can see, dip slopes, and with these you tend to get very large volume planar failures along bedding plains, and sometimes lakes are formed like this. This is at Mangapoiki landslide. So that's the rural area. In Gisborne itself and the suburbs, the landslides tend to be much smaller volume, and they tend to be in residual soil or colluvium, sometimes river terrace material, so that they tend to be much shallower, smaller volume. It's in more rural areas of Gisborne where you tend to get the bigger landslides. So here's a complex here in rural areas, and this is the Te water pipeline. Now this was actually fractured by, I think, in 9 areas in 2023, but mainly not by landslides but by logs that have come down the river. But this is what it looked like in November 2021 with this big complex creeping towards the water. And you know, this water pipeline brings 90% of Gisborne's town water supply. This is 2021, a very big coastal landslide there. The railway, the Napier-Gisborne Railway is along here, which is mothballed anyway, but it obviously won't be opening anytime soon due to big coastal landslides like this, which occurred in the Miocene sediments. You can see dipping out of slope here. So obviously structural geology is really important. And February 2023, Taro Valley, big landslide there. And you can see it's actually within a former landslide as well. So these natural levees have been built by a previous landslide. And this vineyard has been affected there. And Tineroto Road, February 2023, another big landslide there, which has taken the road out. So that's the rural areas. That the suburban parts of Gisborne, they're much smaller landslides, but they can be very damaging. This is at Belgian Terrace. These landslides in suburban Gisborne tend to be early Pleistocene Mangatuna Formation, which makes up the river terraces and slopes. These are cohesive soils, smectite rich, high plasticity, expansive. Failure tends to be generally rotational slumps which transition downslope into earth flows, and they can run out down driveways, onto roads, etc. And one characteristic of Gisborne is there's a lot of paleo relic landslides where people have built their houses on. So you can see here, this is this tennis court here, and this is a former landslide, a relict one, but obviously people built without thinking back in the day, that they're very close here to a lateral scarp, or the minimal setback distance here from this head scarp. And this is just characteristic of Gisborne. Unfortunately, people building in very close to relict landslides, or in fact sometimes on relict landslides. And Balance Street is another example. Houses there, you can just see this is quite coarse LiDAR DEM, but you can see these are all relict landslides here that people have built on. And then this area shows a landslide which occurred in 2021 in this area. Fortunately, and very little setback distance as well, so that means people get evacuated. And that was a characteristic one at Balance and Hill there, with the retaining wall was not substantial enough, very thin planks, very shallow 1 meter embedment depth to about a 2 meter above ground freeboard. No real drainage behind it, so it wasn't really a retaining wall at all. It wasn't retaining much, probably apart from a bit of moisture, and that obviously failed. And retaining walls not built to code are a real characteristic of not just Gisborne but Auckland as well, unfortunately, and other parts of the country. And you can see this landslide ran out across here, and the council put concrete blocks there to try and retain the material and keep it off the road. Clifford Street, another example there of a house built really close to an existing landslide, and then the yellow dotted line shows the landslide in 2021 that formed. Another characteristic is people build a lot of swimming pools close to slope edges and load slopes inadvertently, I guess. Tremendous views, sitting in your swimming pool, swimming around, great views across the city. But loading a slope, or sometimes in some cases, building right to the slope edge with hardly any setback distance, another characteristic. And this is typical, a deck undercut, and the material being channelized down slope and then running out, in this case, to this house here. And one characteristic of Gisborne is a lot of homelessness, or people living in informal areas. So grandparents might be living in a bed in a garage, for example, just due to the shortage of housing, and so garage might be flooded during a landslide or something like that. Debris flow might go, or a mud flow might go down and inundate part of the garage, And unfortunately, then grandma and grandpa haven't got anywhere to stay anymore because they've been living in the garage. So, as I say, there's a lot of poverty in Gisborne and other parts of New Zealand, a lot of homelessness. And these often the material can run out down slope and inundate garages where people actually might be living in a garage. So Matt Cook, I don't know anything about INSAR, so I recruited somebody who was going to be really good at it. So Matt Cook did his masters at Cardiff University, and then I managed to recruit him with my Earthquake Commission funding and get him over to do this INSAR work, which he's done a great job at and published a lot of. So I'll just take you a bit of his INSAR work. He processed it using ICSE, using MINT-PY, and he used the small baseline subset technique in Gisborne. And he looked at ascending and descending Sentinel-1 from 2016 to 2021. And this just shows you the colours here of some of the movement that he was detecting. In many areas up to 50 millimeters a year of movement. And obviously that's enough to deform infrastructure, fixed infrastructure, roads, concrete slabs, if the slab hasn't got enough steel in it. And this is problematic deformation. He found 132 what he classed as landslides, and he had a minimum slope angle of 5 degrees. So landslides can occur in Gisborne on slopes of as low as 5 degrees if it's particularly wet and you've got high pore water pressure. If there's a logging truck going past as well, that can be an effect, dynamic effects from things like that. So he found a lot of landslides in the suburbs, and I think that's caused a lot of people to think about where they might be living. So I'll just show you some of the data. This is a classic one, Richardson Avenue. A house here with a swimming pool there, rotational slumping up the headscarp, and then a channelized mud flow down slope, typical back tilted blocks in these scarp areas, and then run off down slope down towards Richardson Avenue here. Real classic site. And here's some of the INSAR. So this is the descending, and we've got 4 lines here, D1 and D2 within the landslide, just at the headscarp, and points D4 and D3 at either side on the stable slopes. And you can see a similar pattern with the ascending. So the south to north orbit, as opposed to the descending north to south satellite orbit. Quite a bit of deformation with the landslide itself, but reasonably stable slopes either side. So I think this is a good example that Matt found there, a good correlation between the descending and ascending data. And it just goes to show that the value of INSAR, I think, in identifying, stable slopes from unstable slopes. And we've also got cumulative precipitation on here, annual precipitation in these blue bars here, and you can see roughly about 1,200 millimeters a year rainfall, give or take. One thing also Matt noticed was the seasonal deformation of expansive soils. So smectite-rich soils, this sort of lovely pale grey kind of mushy peas, sort of microtopography. And this just shows some of this quite nicely, some of the descending and also the ascending INSAR data, showing this seasonal shrinking and swelling, which can have a strain softening effect over time, I guess. And ultimately, it's not good for infrastructure. I'll just talk here about Russell Street, and this is one we just published a couple of months ago. Ariane Poller, another research student of mine, some CPTs put into this one. The headscarp's around here. 201's built above the headscarp here, and then unfortunately these houses down here, 215, 213, 211 are within the landslide area. 198 isn't, we don't think. So the landslide probably finishes about here where Russell Street actually is. This is the mid part of the landslide where the road goes up. You can see compression in that area. We've got some run out here of a secondary failure downslope. This is some inundation around the back of someone's house. So this is what we think is probably the rough outline of the landslide there. Fortunately, yeah, these houses have been, well, they've been bought out. These people, they got part of the government scheme, which I won't talk about today, but there's a future of severely impacted land, a fossil process in New Zealand where for particular events that occurred in 2023, the government and the council were going to buy out the homeowner. So these houses have been bought out. And this photo just shows you, one of the inspections we did. The the back of the house has been inundated. This is some LiDAR differencing Ariane did, and you can see, about 6 meters of displacement from that headscarp area, and about 5 meters of bulging down slope. And you can see 215 has been nicely tilted down slope, and it shows up quite nicely, that tilting in the LiDAR differencing. And here's some heave here shown by this little scarplet. And this is the landslide here. It had a couple of CPTs put in it by for Ariane's project. This is a rough approximate engineering geological model, I suppose. And we think it's not particularly deep. Otherwise, 198 and 194 would have moved, and there would have been some signs of distress on their properties, and there isn't at all. So it's a reasonably shallow landslide. So I'll just move on. The final case study is Auckland, 2023, January and February rainstorms. So on the 27th of January, it was a Friday. Elton John was due to play at Mount Smart Stadium, I think, Friday evening. And it was Auckland anniversary weekend, so a public holiday on the Monday. And then a major storm then, and then that was a 1 in a 200 year storm in central Auckland probably. And then 13th to 14th February at Muriwai on the west coast, this area, actually Piha and Karikari as well, possibly a 1 in 250 year rainstorm then. And January actually was, in central Auckland, was the wettest month in Auckland on record, January 2023. I think records began in about 1853, I think. So this is Auckland. Central Auckland is all Quaternary volcanic field, 53 volcanoes. And then this yellow and orange, this is all Miocene volcaniclastic sediments. And also some lavas and other associated volcanics. So I'll just take you through a couple of landslides. I should say in Parnell in central Auckland in January, there was a fatal landslide. In Muriwai in the following month, there were fatal landslides. Unfortunately, at Muriwai, 2 firefighters died in that landslide. This just shows you what happened in 2023. This is central Auckland, or Auckland Airport, I should say. These are the curves going back, I think, to about 1960. I think I've got that right. 1963, 2022, and then we've got 2023 on it. These are just cumulative, the first few months of the year, and you can see, 2023 is a massive outlier. Here's the Auckland anniversary storm, where we had 211 millimeters in 6 hours. And here's the 13th of February Cyclone Gabriel, where in central Auckland there was substantial rain, but actually, out on the west coast is where most of the rain happened, 147 mils in 12 hours. And then the tipping bucket rain gauge actually failed, unfortunately. But possibly it was a 1 in 250 year event in West Auckland. This is the first fatal landslide in January in Parnell. This is just this area here. This is Shore Road. The landslide came here down from the Miocene bedrock, and residual soils behind impacted this house. Unfortunately, the gentleman died. This is a cliff line, and these are house prices. So, it's quite incredible. But just due to the cost of land in Auckland, if these are in New Zealand dollars, if you divide it by 2, you get it in pounds roughly. So, this house here, it's just crazy prices. There's 2.6 million pounds roughly that. This one is probably about 2.6 maybe million, and you can see hardly any setback distances. These are just timber with a tin roof. And And it just goes to show, the cost, just the cost of housing is such that people will, live in these areas because they think they've got a nice view. So the wealthy people will buy here and think it's, it's a wonderful view, but there's very little setback distance. And also at the toe of the landslide, at the slope, there's very little setback distance at the toe. Unfortunately, there's a landslide in 1997 here, or just one door down here, 35A. And in fact, we'll just show that here. So this is 35A landslide 1997, and this is what happened in 2020, in 2023. Just historical pictures there. Just quickly, Muriwai, West Auckland. This is Cyclone Gabrielle, February 2023. Pliocene escarpment, sandy escarpment or Pliocene, and early Quaternary sandstone escarpment. Lots of previous landslides. In fact, 1965, this dark grey landslide. 2023, landslide in the same area, as well as landslides here, and a fatal one here, unfortunately. Very steep escarpment. It's basically a very large sand dune. These are, Fitter group dune sands, weak, uncemented. And when they fail rapidly, 5 meters a second. We've got a gentleman here just walking through, the aftermath. And this is a cross section from Matt Howard's paper that we just co-published recently. It shows you the topography there and some of the issues. Unfortunately, this is a classic case here of deregulation. So the Local Government Amendment Act 1981, this deregulated planning, and it removed legal liability from councils for allowing building on unstable land. So even though, landslide occurred in 1965, 2023, a landslide in the same place. This outline is the 1965 landslide, and you can see there, 1963, people building there or built there. By 1969, the landslide happened. It's all emptied out, no houses anymore, all been removed. By 1982, people start building within that footprint again, unfortunately, and this is what got inundated again in 2023. So that was that's a legacy effect, unfortunately. Now, just to finally summarize, I'll just bring this together. I think we've got a big problem with vulnerability to landsliding in New Zealand, and we throw millions of dollars at research that, we all publish papers like good soldiers on landslides and all the rest of it. And we can keep throwing all this money at it and everything. But the problem is the legal situation in New Zealand. And we've had a lot of positive legislation in New Zealand to try and mitigate the effects and decrease vulnerability to landslides and other natural hazards. But unfortunately, we had deregulation in 81, and we had with the Building Act in 2004, Section 72, that allows councils to permit building on unstable land. It may mean that there's a note goes on the property file or the title, but the councils can still allow building on unstable land, and property developers will go to court to force councils to permit building. And there's very little councils can do sometimes to push back. They have very limited means legally. And, property developers have got, very, expensive barristers, King's Council, all the rest of it. And the price of housing, $5 or $6 million, £2.5, £3 million to get a nice view, people will pay to force the council's hand and allow building. So it's a real problem. Just quickly, we've got a good conference going on in Queenstown next year. This is part of JTC1, JTC3 coming together on landslide and geoeducation and risk, Lager 2026. We've even got a special beer getting brewed for us for that conference. So please consider attending. There's go on the website, have a look. It should be a good one. Some great field trips too. Just to acknowledge the research students involved who've been great, and also my generous funders. And that's it. Hope you enjoyed it.
Super, Martin. That was really interesting. Thank you very much. Does anybody have any questions? Yes, Ahmed, I can see you've got your hand up. Can you unmute yourself, or do I need to do that? Let me Let me see if I can unmute you. I think you're going to have to type your question in the chat, everybody. The way this meeting has been set up, I don't think anybody else can unmute themselves. Sorry.
Are you able to hear me, Paul?
Oh, yeah, I can hear you, Roger.
Yeah.
All right. Okay. Hi, Martin.
Hi, Roger.
Yeah, great to see you, and fantastic presentation. New Zealand really does have it all, you know, when it comes to landslides, doesn't it? Yeah, it's got everything. Absolutely fantastic. I guess a couple of things I was quite struck by. I think in the early part of your talk, you showed some sections through the leader landslide.
Yeah.
And looking at the fairly relatively shallow angle on the basal shear, there does appear to be, you know, these appear to be quite high mobility landslides, don't they, with quite long run out.
Yeah.
So I guess, you know, one of the question around that probably comes down to the materials, plus also the earthquake motion perhaps is all part of that.
Oh, yeah.
Perhaps you comment on that in a minute. And my other one was around the rainfall. And again, some of those rainfall charts that you showed, you accumulated rainfall by year. But you chose January, I think, as the year. But as I understand it, the seasonality in New Zealand isn't quite, say, like the UK. Is it from sort of, was it June, October? Is the peak winter period. So I guess there's a question there around the seasonality of the rainfall and effect of antecedent as opposed to intense rainstorms, whether you've got anything more to say on that.
Yeah, well, start with that. Yeah, the antecedent effects are really important. And I think New Zealand is a place where the rainfall thresholds, you know, it's part of the picture, but it's the antecedent conditions which are the big part of it. You know, if you've got an existing perched water table and then, you know, 100 mils in 24 hours or perhaps even less than that, then there's going to be a problem, that sort of overprinting or layering effect. So yeah, the antecedent issue, you know, that conditions are super important, and I think that's why a lot of people move away from just thresholds. It's too blunt an instrument. Regarding the earthquakes, so Caleb's done a fair bit about the directionality of the seismic waves, which I didn't talk about today, but I know in his papers he does talk a bit about the directionality from the epicenter and interactions with the topography in some of those big bedrock landslides he looked at. Yeah, so that's important, I think.
What about the material properties? I presume we're looking at quite low mobilized shear strengths with some of these materials.
Yeah, and I mean, well, in the rock, yeah, and I think you've got to think these have been deformed by a succession of earthquakes over the hundreds of thousands of years. So, I mean, some of the rock mass conditions that he was looking at, I mean, and some of the dilated material, it's weak material. So I think, you know, that's a factor as well. And in some of the areas, the more shallower landslides that are, you know, more rainfall triggered, I guess a lot of the materials already has remolded strength. And certainly in Gisborne there with the rainfall triggered landslides, I mean, Matt Cook was identifying landslides and movements on slopes less than 10 degrees. So the materials has remolded strength. You know, if there's antecedent rainfall, then, you know, then a storm event comes through, and, you know, maybe there's some logging trucks going up and down the road. These are all, you know, it's the interplay of several effects, I guess. Yeah.
You two can carry on this discussion on the eggs field trip at the weekend. We've got a few other questions in the chat. So James Codd has asked, has there been any more work or developments on the Lurse landslides in the Port Hills and Banks Peninsula area in the last 10 years?
Yeah, there has. Catherine Yates at Canterbury University published a good paper with Clark Fenton about 2 or 3 years ago in Engineering Geology. So there's that. That would be one to look at, and I think there might be one published last year as well. Oh, in fact, yeah, sorry, yeah, New Zealand Journal of Geology and Geophysics, actually a special issue I've just edited. There's a paper in there as well.
Super.
Yeah.
Thank you very much. Stephanie Kirkman has asked, do you think you're starting to see any shift in the legislative planning for resiliency against these kinds of landslides events, or is that still, an ongoing journey to change mindsets?
Stephanie, former student. Hi. Look, I think the change of government possibly hasn't helped. I think we're probably on track for a few good things with Labour. The new government came in. I'll leave that there.
So what does it take to change mindsets when you have landslide fatalities? What more can you do to change people's minds? People
have short memories, very short memories, and because there's so many people want to own a home in New Zealand, and it's very hard to get on the property ladder. People will buy absolute lemons of houses. And even if it's got a note on the property title saying it's on land subject to hazards, they'll somehow try and make that purchase. They might struggle to get a mortgage potentially, but
can they get insurance? Can you insure against those things in that
context?
Yeah,
well, you can. I mean, there's a bit of insurance retreat now. Insurance premiums are going up, but I guess you shop around and see if you can get a policy. Yeah.
Super. We've got a question from Josh Jones, picking up on the Parker et al. 2015 paper, talking about earthquake preconditioning for coast seismic landslides on South Island. He's asking whether the wealth of landslide inventory data that's been collected subsequently really brings that story any further forwards.
Yeah, it does. All the stuff that Chris Massey and Colin Bloom have published, and Corin Singerson and Caleb as well. That Parker et al. Paper is heavily cited, and that preconditioning effect. Yeah.
And Karan Navneil has said, has been any studies on the correlation of slow slip events on the Ikarangi subduction zone contributing to landslips in the Gisborne Hawke's Bay area?
We've done that, and we did it with emergence of mud volcanoes as well. It's I think we're the only one who looked at it, but it's qualitative and it's hard to pick out.
Super. No more questions in the chat, so thanks everybody for your questions and your contributions. Thanks again for Martin for spending the time to talk to us today. Just a reminder, the next BSG Eggs talk is on the 24th of June with Mark Lee presenting his talk, Geomorphology, Geohazards and Energy Pipelines. So thanks everybody, and see you at the weekend, Martin, on the field trip.
No worries. See you, everybody. Thanks very much. Bye-bye.